Hello and welcome to our lesson on set theory. We're going to go into the basics of sets, some vocabulary and concepts that hopefully will help you moving forward. So a set is just a collection of people or places or things. Maybe an all-encompassing word could be objects, and we're going to call those the elements of the set. So again, a set is just a collection of people, places, or things, and those are going to be referred to as the elements of that set. And then we have a symbol for element, looks like an E, it's sort of a curved E there. So it's a pretty natural process for humans to group things, right? To group things into sets, to group people into sets or places or things. So this grouping concept, again, is what we're doing with sets. Now, when we group into sets, the order of the elements in the group or in the set doesn't matter, but the way that we actually define it does. So there are three ways to write or define a set. We can just give a description for the things that we're grouping in a description form. We can give a roster form where we list out the elements that are in the sets in braces. And then we have this really mathematical one that we call set builder notation. So I'm going to show you some examples. So for example, in the first one, if we're looking at the set of all of the integers, okay, all integers, that's a pretty mathematical thing. Those are a set of numbers. That would be the description form for that set. If I wanted to give the roster form for that set, another way to define the set of integers, then I would actually list out in braces what the integers are. Now, if you haven't classified numbers in a while, the integers is an infinite set of numbers, so I can't possibly list the entire roster, but I can do something like this. The integers, again, if you haven't classified numbers in a while, these are all of our positive and negative whole numbers. So no fractions or decimals in there, but positive and negatives and zero, those are there. So I'm going to use the ellipses ... because I can go forever in both directions with these. I have numbers like -2 and -1 and 0 and +1 and +2, and I can keep going again in both directions. So that would be a roster form for that set, just a list of the numbers that are in that set. Now in the set builder notation, this again is a pretty mathematical one. We have these braces again, but instead of listing out the individual elements in a roster form, we're going to use this notation, and then we're going to give a description. So what this notation says is we're looking at the set of all x's such that some criteria is true. So when I'm reading this, this is going to be the set or of all x's such that. So all x's such that is how we read that first part of the notation, and then here is going to be the criteria that's true. All x's such that some criteria. And this is usually used for mathematical sets. You'll see when we get to the last example, it doesn't really apply nicely to something that isn't mathematical, but we can use all three of these forms in any case. So let's continue to work through the examples here. So the description, we have the set of all integers. We got a roster where we sort of listed out what those look like, and now the set builder notation would be we want the set of all x's such that. So that part will never change. It will always look like that. What's going to change is the description or the criteria, the thing that is true about the numbers in that set. So here we want all x's such that. We want all integers or numbers such that. Our x's, our numbers in this case, are elements of the integers. And the integers we use the capital letter Z to represent. And so that's what our set builder notation would look like there. And if you wanted to say integers here because you didn't know the symbol for integers, that would be fine. Okay, so that's what our set builder notation looks like. Let's try that again. So let's say we're looking at the set of integers that's greater than -2. Then if I wanted to roster those out, greater than -2 means we're not going to include the -2, just all the integers that are greater. So the first integer on the list then would be -1, and I couldn't go less than that, so there won't be any ellipses on that side. So I have -1, and then 0, then 1, then 2, then 3, and I could just keep going with my integers as long as they are greater than the -2. So there's how my roster would look. And now I want to say for my set builder notation a couple of things. I have all x's such that. So x, again, x could be numbers, people, places, things, whatever the objects are, we're just going to call them x's. And then we want to say what's true about the x's. So in this case, we're dealing with integers again. So I still want to say my x's are elements of the integers, but it's not all of the integers. This time it's only the integers that are greater than -2. So now I'm going to put that second criteria in here. Again, these x's have to be greater than -2, and that would be the set builder notation. And I'm really not good at drawing these braces for some reason. Drawing the one on the right is harder for me than the one on the left, so excuse my braces. Let's try this again. So we're looking at the set of integers, this time just between -4 and 2. So if I was going to roster these out, the integers between -4 and 2, again, wouldn't include the -4 and 2, just the ones in between. So the -3, -2, -1, 0, and 1. And no ellipses, because I'm not anything less than -4 or bigger than 2, just strictly that roster of numbers, that list of numbers between, the list of integers between. So there's our roster. Now I'm going to say this is all x's such that, in this case, our x's, our things, our objects, are again integers. So we're an element of the set of integers, and this time we're between -4 and 2. So I want to put my x between -4 and 2. I want to be greater than 2, and I want to be less than -4. So we make a double inequality there. And I don't want to get too hung up on this mathematical one. In the examples that you're going to see in your assignment, we won't get too into the math here. I just want you to have the concept down, okay? Now, if we look at the last example, we're looking at a set of months beginning with the letter M. So if I was to list those out, a roster of these elements, months that begin with the letter M. So we've got January, February, March, begins with an M, April, May, June, July, August, September, October, November, December. That's going to be it. So just these 2 months. The roster works out pretty nicely. And these two forms are always going to be a nice way to define or write out our set. When our set is not really mathematical, like this last one isn't, the set builder notation isn't typically used. We can still do it. It's just a little silly. So for example here, we're going to say, now I can't draw the brace on the other side. This is all x's such that. I don't have any mathematical notation to describe the months that begin with the letter M, so I'm just going to give the description. So I can, and actually I could just list out March and May, but I'm going to say X is a month beginning with M. So it seems a little silly again to do this because it's really just the same thing that we have in the description form, but with that set builder notation. The set builder notation is mostly used for math, but again, we can apply all three of these to really any set. So a set, again, is just a collection of people, places, or things, or objects that we're going to refer to as the elements. We can write this in a description, in words, in a list that we'll call the roster form, or using that set builder notation. All right, so some properties of sets that we need to be familiar with. First of all, when we are creating a set, at least in mathematics, but in general, we want it to be well-defined. For a set to be well-defined, it means its elements, the things that are in that set, should be clearly identifiable without any opinion or guessing involved. So if I said, for example, the set of students in a class, that is something that I could clearly roster out. If I asked every person in the class to make a set of, or to write the set of the people in the class, they would all write the same set. Now remember, the order that they wrote down the students might change, but the order in a set doesn't matter, but everyone's set would look the same. Now if I said to write out the set of the best students in the class, the students that I think are the best might be different from the students that you think are the best, and they might be different from the students that someone else thinks are the best. So we might be creating different lists because there's some opinion in that word best. What I think is best is different from what you think is best. So this first one is an example of a set that is well defined. which is what we want. And this one is not well defined. We do not want that. We don't want any guesswork or opinion in the sets that we are defining. Okay? Once we have established we have a well-defined set, it's possible that that well-defined set has a countable number of elements, and it's possible that we can't count the number of elements. If it's countable, it's what we call finite. If it's not countable because the elements go on forever, they're impossible to count, then we're going to say it's infinite. And we saw that in these sets we defined just a few moments ago. So this is an infinite set of numbers. The integers go on forever. So that's an infinite set. Again, this list goes on forever. This list is countable. It does not go on forever. It's just those integers between -4 and 2. And this list is countable. It does not go on forever. There are exactly 2 elements in that set. So again, the integers between 1 and 10, if I was to roster those out, if I was to roster those out between 1 and 10, I have 2, 3, 4, 5, 6, 7, 8, and 9. That is a countable number of elements, so we'd say that this is finite. If I wanted the integers that are greater than 1, again, if I was to roster those out, that'd be 2, and 3, and 4, and 5, and that list would just keep going forever. So this is infinite. I couldn't possibly count how many elements are in that set. All right, now, if a set is finite, if we can actually count the number of elements in the set, then that number of elements that's in the set is going to be referred to as the cardinality of the set, or the cardinal number of the set. So the number of elements in the set is the cardinal number, or again, the cardinality of the set. And the symbol for the cardinality looks like this. It's an N and then in parentheses. So for example, and we don't always use that notation, and I'll show you when here. So for example, if we were looking at the set of days in a week, there are obviously 7 days in a week, so we would say that the cardinal number here, the cardinal number is 7, or we could say that set has a cardinality of 7, but that set isn't really named. Whereas if you look at the second example, it says set A is the numbers 15, 16, and 15, 16, 17, and 18. So since this is named, we have a name for this set, it's set A, then we can use the notation. We can say that the number of elements in set A using that symbol, that notation, would be 4. There are 4 elements in set A. And this same is true for the next example. So we have set B, a name for this set. It includes the elements circle, square, and triangle. That is 3 elements rostered out in that set. So we would say that the number of elements in set B is 3. We could also just say, like we did in the first one, that the cardinal number for B is 3, or we could say for the second one that the cardinal number for A is 4. But when the set is named, we will generally use the notation to say the number of elements in that set is whatever that countable number is. Okay? So we've got that notation for the cardinality or cardinal number of a set. Now, if a set doesn't have any elements, or if it's got a cardinal number of 0, we call it the empty set. The empty set, or sometimes we also call it the null set. I tend to use empty set, and there are 2 symbols for this. One of them you've probably seen before. Looks like the no solution symbol that we're used to when we solve. We use that symbol to replace the words no solution, because if we solve an equation that doesn't have an answer, it means that the set of answers is empty. There are no answers in that set of answers. We can also, for empty set, use the braces and just don't put anything in them. That would be, again, a symbol for an empty set. Okay, now if we got a set that has no elements, we can also have a set that has all of the elements. If a set has all of the elements for whatever topic we're referring to, we're going to call that the universal set. So suppose I was talking about dogs and cats. Maybe dogs and cats are elements of pets. So if our universal set is all of the pets that are in the world there, then dogs and cats might be elements of that set. So whatever our topic is, if I wanted to include all of the elements for that topic, they would be included in the universal set, and we can use a capital U as a symbol for the universal set. All right, moving right along. Now that we've got some vocab out of the way, let's add some more. A subset is another concept that we'll see pretty frequently. A set is going to be considered a subset of another if all of the elements are in the other. And I think the concept is probably intuitive. So again, if my universal set is all of the pets that are in the world, the dogs might just be part of that set, right? All the cats might be just a part of that set. Birds might be a part of that set. Hamsters might be a part of that set. So subsets are going to be sets that we can create from other sets. So all of the elements in a set, if they're in another set, it's a subset of that set. Now I'm going to say the word set 80,000 times. I'm so sorry. A set is a subset of another if all of its elements are in the other. So you can think of a subset as a set being made from or coming from another set. And we have a symbol for subset. It sort of looks like a sideways U, and it is underlined. Underlined because a subset can be equal to the original set that it's being made from. And it's important to note that the empty set is technically a subset of all sets. The empty set, remember, that's the set that's empty. It's got nothing in it. It has no elements. I can make a set of nothing from any set. Whatever set I'm looking at, if I wanted to take nothing from it, I could do that. So we're going to say by definition that the empty set is a subset of all sets. All right, so let's get an example and try to wrap our brain around the concept here. So we've got a couple of sets defined here. Set A includes the elements 1 and 3. Set B includes 1, 3, and 5. C is 1, 3, 5, and 7. D is 1, 3, 5, and 7 as well. So is it true that this is happening? So when we're reading that, we're going to say set A is a subset of B. That means, are the elements of A in B? Could I make this set using this set as the original? So could I make set A from the elements that are in set B? Well, yeah, A has 1 and 3, and those are in B, which has 1 and 3. So I could make this set from this set, which means it is a subset. So this is going to be true. Okay, is B a subset of C? Could I make set B using the elements of C? Yeah, because 1, 3, and 5, they're here. So again, this is going to be true. Is A subset of C? Again, could I make A from C? Yes, I could. So this is going to be true. And then is C a subset of D? Could I make set C using the elements of D? Yeah. And I know those are exactly the same, but I could make C from D, so this still works. This is going to be true. Now if I flip these, if I say or ask, is B a subset of A? Could I make B using just the elements of A? No, because B has 5 in it, and I can't get that 5 from A, so this would be false. Could I make C, or is C a subset of B? Could I make C using the elements of B? Nope, not possible. So again, this is going to be false. I cannot make C that includes a 7 using B when B doesn't have a 7. Okay, is C a subset of A? Could I make C using just the elements of A? No, I cannot. So this is going to be false. And is the empty set a subset of C? I don't even have to look. That's going to be true because the empty set is a subset of all sets. All right. So the concept of subset we can make just a little more specific with something we call a proper subset. Proper subset is almost the same. It's a subset, right? That's part of the name here, so it means we're making a set from another set. But the distinction here is a proper subset cannot be equal. A set is a proper subset of another if it is a subset that is not equal. So again, these would be considered subsets of one another, but if I wanted a proper subset, then they shouldn't be equal. If I'm properly making a new set from another, I don't want to make the exact same thing, okay? So the symbol for proper subset, again, looks like a little sideways U, but it doesn't have the underline. So underline means we can be equal, that's just a subset. I take the underline away, that means not equal, that is a proper subset. Okay, so same sets in this example, we just want to see now, are these proper subsets? Is A a proper subset of B? Can I make A from B? Yes, it's a subset. Is it proper, meaning not equal? Yes, so this is a proper subset. Is B a proper subset of C? Can I make B from C? Yes. Are they equal? No. Perfect. This is a proper subset. Is A a proper subset of C? Yeah. Again, I can make A from C and they aren't equal. So this is true. Now, is C a proper subset of D? It is a subset. I can make C using the elements of D. But since they're equal, C is not a proper subset. It is a subset, but it's not proper. So this would be false. Okay. It's a subset, but not proper. Alright, so I've thrown a lot of vocab at you. I just want to make sure that it's sticking. So let's do a little vocab check here with a few more examples. So the first statement in this box says that the set, because this is in braces, the set 3 is a subset of the set 3, 4, 5. So just what we were doing a second ago. Could I make the set 3 out of the set that contains 3 and 4 and 5? Absolutely, this is true. Now, you notice a distinction between that first example and that second example. The next one says 3 is a subset of the set 3, 4, 5. If I take the braces away from the 3, then it's not a set anymore. It's just a thing, an element, right? And only a set can be a subset or proper subset of another set. So this is going to be false. And this is going to be false because 3 without the braces is just an element, and only a set can be a subset of another. So 3 is an element, not a set. And again, only a set can be a subset of another. So if I wanted to make the statement correct, I would change the symbol. I would say 3 is an element of the set that contains 3, 4, and 5. So now this is true. All right, now let's change the symbol again. If I said the set 3 is an element of the set 3, 4, 5, not true. I don't want that set to be an element of the set 3, 4, 5. The elements of this set are just a 3 or just a 4 or just a 5. Okay, so 3 is not an element. It is a set. So this is going to be false because, oh my gosh, with the braces. 3 is a set, not an element. And then I'm going to get real tricky here. When we look at the next example, here I have a set, and we're asked if it's an element of this set. But look at the elements that are in the set. The elements are sets, right? In this one set, I have 3 other sets. The set 3, the set 4, the set 5. So this one's actually going to be true because the elements of the set that follow there are actually sets. So this is going to be a true one. Really tricky. And I'm not going to, in your assignment, give you anything that's this ridiculously tricky. I'm just really trying to make sure you understand the symbols. Okay? Empty set's a subset of anything, so I know this is true. Again, empty subset is a subset of anything. Is it a proper subset? As long as this is not also the empty set, so these two can't be equal, then that's still going to be true. Now, is 7 an element of the set 3, 4, 5? Obviously not. There isn't a set 7 in this list of elements, so this is going to be false. 7 is not in the set. And obviously the set 7 is not going to be a subset of this if that's not included there. So that seems kind of silly. Again, 7 is not not 7. Set. Oops, went too far. Okay, here we go. 7. I cannot with these braces. 7 is not. The set 7 is not a subset. I'm really falling apart in this last example. Okay, so I'm not going to try to give you anything too tricky. Again, I just want you to make sure that you understand the symbols. For the most part, if you have a basic understanding, you should be fine for your assignment. But if you have any questions, then please reach out. Until next time, take care.